trying to figure out where Michal is.
Michal is here. This is Michal.
היי מיכל, מה העניינים?
היי, בסדר.
רגע, אז את יושבת יחד עם אינגריד?
כן.
הבנתי, יאללה, שתי ציפורים במכה. בסדר. סיגל, תני לי איזה איתות אם אפשר להתחיל. אוקיי. אוקיי, ככה, ערב טוב מישראל, צהריים טובים בארצות הברית. שמי שמוליק, אחד מהמייסדים ובצוות ההנהלה של ביו-אברוד. הפגישה היום תהיה רובה באנגלית, כי אינגריד היא דוברת רק אנגלית. אז אני אתן קצת כמה מילים בעברית ואני אעבור לאנגלית ברשותכם. הסמינר של היום הוא אחד מהסדרת וובינרים בעניין של יזמות. היה אחד לקראת סוף שנה שעברה, זו השנייה ומתוכננים עוד כמה שאנחנו עובדים עליהם. הוובינרים האלה מבחינתנו הם מאוד מוצלחים עד היום, כל הנושאים שהעלינו הייתה עיינות גבוהה, ואנחנו מאוד מרוצים ואנחנו מאוד מודים לכם שאתם משתתפים ונהנים. אני אעבור קצת לאנגלית עכשיו, אני אציג קודם כל את הספונסרים של הערב הזה, את הדוברים, ונעבור לעניין. כמו תמיד אפשר להעלות שאלות בצד, כולכם במיוט, אבל אפשר שאלות בצד, ובדרך כלל אנחנו משתדלים להסתכל הצידה ולהתייחס תוך כדי אם יש שאלות או הערות שהם חשובים להגיב עליהם. Okay, so I'm going to turn to English a little bit because, as I said, not all of us speak English, Hebrew tonight. So first of all, let's talk about our co-sponsors for tonight, for these events. These events apparently all cost, so we need sponsors. So tonight's sponsor is the MIT Israel program. The MIT Israel program aims to strengthen connections between MIT and Israel. Its main component is a 10 to 12 week internship program for students, researchers, MBAs, and recent graduates from MIT and companies and universities in Israel. This year, MIT Israel sent over 75 students to Israel. MIT and its students have a special interest in biotech-related internships in Israel, and the program can recruit students from specific fields at MIT. For companies and labs, this is a unique opportunity to get access to MIT students and information to technology transfer. Currently, MIT Israel has arrangements to enable MIT students to do 10 to 12 week internships at many labs at universities in Israel and at Endospan, Orbimed, Protalix, Rambam Hospital, Teva, and many other small and medium-sized companies. Host companies provide a stipend to cover internship costs. Anybody interested, please contact David Olev, and we have his email, his contact info, so anybody that's interested can call us if there's anybody here from Israeli industry or universities. Keynote speakers today. First one will be Dr. Ingrid Beattie. I hope I'm pronouncing the last name correctly. And Dr. Michal Preminger. A little bit about Ingrid. She's a member in the intellectual property section of the law firm Mintz Levin. Her practice emphasizes patent prosecution in the area of biotechnology, particularly in the fields of molecular biology, immunology, microbiology, cardiovascular medicine, clinical diagnostics, and medical devices, and includes advising clients on issues relating to patent portfolio management and licensing. Prior to joining Mintz Levin, Ingrid was a technology transfer associate at the Dana-Farber Institute, and then practiced at another prominent Boston law firm. She has served as the president of the Boston Patent Law Association, is a member of the Licensing Executives Society and of the Association of University Technology Managers, and has been recognized in Massachusetts superlaves as a rising star in the field of intellectual property. She holds a PhD in immunology and microbiology from Emory University School of Medicine in Atlanta, Georgia, and a JD from Suffolk University in Boston, Massachusetts. Michal, Preminger is Executive Director at the Harvard University Office of Technology Development, overseeing the Harvard Medical School site. Prior to joining Harvard, she held a number of business development and technology development positions at Compugen, most recently as a Vice President of Protein Therapeutics, responsible for the business management of the company's emerging drug discovery pipeline. Previously, Michal had held several marketing and business development in the high-tech industry, among others for Lucent Technologies, and co-founded a biotechnology startup. Additionally, Dr. Preminger has served in the past and present as a member of the board of directors in multiple companies, including, among other, Alma Lasers, BioArray Therapeutics, and Elminda, and as the member of the Scientific Advisory Board at Pfizer for Life, a not-for-profit organization focused on the promotion of research in the area of ALS. Dr. Preminger holds a PhD and a Master's in Biological Science from the Weizmann Institute of Science in Israel, a Bachelor's degree in Medical Science from the Hadassah Medical School, Hebrew University, and an MBA from INSEAD in France. Having said all this and introducing everybody, thank you, Ingrid. I think you're the first one to start. Thank you again, and go ahead.
I am. Thank you very much. So yes, I will present first, and then Michal, and I think probably best if we save questions until both of us are finished with our presentations, if that's okay. All right, so the topic of my talk today is protecting and commercializing intellectual property. So the first question is pretty basic here, how to protect intellectual property. Patents, of course, and that will be the subject of my talk, but just for a little bit of context, trade secrets is essentially an invention that you could choose to patent, or you could choose to simply keep it secret, keep it limited to a very small amount of people, keep the design or the formula or what have you under lock and key. The most famous trade secret is actually the recipe for Coca-Cola. Copyrights, simply a means to protect works of authorship, printed publications, art, drama, written music, that sort of thing. And trademarks simply being a source identifier, where your product comes from, like Kleenex brand tissues. So next slide here. Oh, I'm sorry, I forgot to do the slides here. There are the 3 or 4 different kinds of IP. Next slide. So what are patent rights? It is a definition of your technology in a way that defines what you can exclude others from making, using, or selling in the United States. In the United States, the term of your enforceable rights are 20 years from the date of filing. More importantly, and for the purpose of this talk, it is the vehicle that drives your invention from the academic lab to use in the real world. What are the steps to getting a patent? Well, the first thing is you make an invention. So what's an invention? You say you work in the lab and you discover that X binds to Y in cancer cells, but not normal cells. Is that an invention? Well, I would say, no, that's not an invention. That is a scientific discovery. What an invention would be a method of treating cancer by inhibiting X binding to Y, or blocking X binding to Y. In other words, it's a use, a manifestation that is based on a scientific discovery. So next step, you call up your technology transfer office. They either have an in-house patent attorney or they call someone like me, and we work together with a scientist to draft a patent application. And the goal of that patent application is really to take that scientific discovery, which usually is in the form of a manuscript or an abstract for a meeting, and find out ways to claim it that can actually be sold, that are commercially developed. You file a patent in the U.S. Patent and Trademark Office. You prosecute it, and that means you essentially communicate with and argue, if I can say that, with the patent examiner to convince the patent examiner that you are entitled to get some claims that cover a commercial product. It takes a long time. From the moment you file in the U.S. Patent and Trademark Office, it can be 2, sometimes 3 years before the patent application is even picked up for examination. So important to think about timing. And then from the first office action, it can be 5 to even 10 years, hopefully not up to 10 years, but it's happened, before you get an issued patent. That's important because you have nothing enforceable until the patent application matures into an issued patent. So how much does all this stuff cost? Generally speaking, it costs between $5,000 and $15,000 to prepare an initial patent application, from a disclosure, for example, of a manuscript for a scientific journal. So it's not inexpensive. Then to argue back and forth with the patent office, generally speaking, $3,000 to $5,000 per volley. And when I say per volley, is patent examiner says, I reject the claims. We say, no, you're wrong in rejecting them, and here are all the reasons why you should give us a patent. Typically, there's at least 2 back and forth communications like that. So add that to the tab. And then once we finally agree with the patent office that we have issued allowable claims, then there's some fees that ensue for actually getting an issued patent. So all in all, it can take $20,000 to $40,000 before you have enforceable rights. So next, I'm going to quickly go through kind of what are the sections of a patent, and we'll look at the front page of an actual issued patent, and you can actually get just a wealth of information from the first page of any issued patent. So the first page gives you sort of data, information regarding the invention, not the scientific part, but the logistic part. There are drawings, which typically are the figures, correspond to the figures in an academic publication. The specification typically is the description of the results that correspond to the body of a scientific publication. But more importantly, what the patent attorney does is really describes then, as I mentioned, not only the scientific discovery, which corresponds to an academic paper, but the invention itself, which corresponds to the methods, the compounds, the use, how you would use that scientific discovery for the practical good. And then lastly, and the most important point, is the last couple of pages of the patent application are what numbered sentences. They are the claims, and they define your legal right, what you can exclude others from doing once you have an issued patent. So the next page here is, and hopefully that is clear enough to read, is the first page of a patent application. You have the title there. This one is Scaffolds for Cell Transplantation. The title can be manipulated to either make your patent easy to find or difficult to find. And that's a strategic move. Maybe you want to be found, maybe you don't want to be found. Just bumping up a little bit, this is just sort of a little bit of trivia here. Here the inventor is Mooney et al. If you go down to just a couple of lines, you'll see the inventors are listed, and there are a whole bunch of them. And each of those inventors has equal rights in the claims. In other words, the order legally is irrelevant. The order practically, however, is quite relevant, because the first listed inventor is always listed on the top, and so forevermore, this particular patent will be referred to as the Mooney patent. So sometimes it's important, just practically and politically sometimes, to decide who will be the first named inventor. Next category down, the assignees. That tells you who owns the patent. In this case, it's 2 academic institutions, and in the United States, if there was federal funding and also policy of universities in this country mandate that the inventors must assign or give ownership of the patent rights to the academic institution, the university that employs them. Scrolling down to item number 22, that's the filing date. That's the date by which you calculate the term or the length of the enforceability of the patent. And then the next section I want to call your attention to is item number 56. You see a big long list of references, and some of them are patent references and some of them are journal articles. When we file a patent application, we have an affirmative obligation. Not only me as the patent attorney, but you as the researcher must disclose to the patent office anything that could be relevant to the patentability of the claims. You make a list. It's submitted in the form of an information disclosure statement. We send it into the patent office. That is one of the first places that the examiner looks to evaluate whether you've got something new and non-obvious, which we'll talk about in a second. The other things that are on this list are pieces of public information, either patent or journal articles that were published that the examiner found. The examiner does his own search. In addition to us telling them what's relevant, the examiner does a search, and that also appears on this list. This list is very important because the claims are deemed to be patentable over anything that's listed here on the front page of the patent. But it does not make the representation that it's patentable over everything in the world. So, for example, if somebody wanted to challenge your patent, if they could find a reference that is not on this list that describes that which you have claimed, they could essentially file papers in the patent office and try to attack the validity of this patent because that piece of prior art was not listed here. So the game for the inventor and the patent attorney is to make this list as comprehensive as possible because you have a presumption of validity over anything that's listed on the front page here. And then just sort of a little bit of trivia, if you scroll on the right-hand side, you scroll down, you see the examiner, Scott Long, you see the name of my law firm and my name. You can search in the patent office under those criterion if you want to find out what kind of patents this examiner has examined and allowed. And you can do the same thing with me. You can put my name into the patent office search engine and see what kind of work I've done. So if you're looking for a patent firm, that's kind of a nice way to figure out what they're good at. Okay, next is sort of what are the requirements for patentable invention? The first one seems pretty self-evident. It must be new. In other words, a single published reference should not have disclosed or described exactly what you are seeking to patent. The second one must be non-obvious, and that simply means that the examiner doesn't have to find one, but he can find two or more publications and put them together and say that the average person working in the field would take a look at these 2 or 3 references, read them, and say, what the people are trying to publish is completely obvious. Anyone in the art, after reading these 3 references, would come to the same conclusion. The next category here is it must be useful. Now it seems kind of a silly thing to be a requirement, but let me just explain it. The invention must have a practical purpose. And as an example, many years ago, about a decade ago, when people were trying like crazy to file patent applications on DNA sequences. People were cloning and sequencing, and everyone wanted to stake their claim to something of value, and very frequently they didn't know what that DNA did. They didn't know what it encoded. They didn't know whatever open reading frame they might find, what that resulting protein would do. Well, guess what? The patent office came back and rejected a whole lot of those applications saying, if you don't know what this DNA does, it is not patentable because it is not useful. And that use must be specific. In other words, it cannot be non-specific. I will use DNA to smear it on my skin and use it as a sunscreen. That doesn't work. The last thing here is it must be enabled. By enabled, that word simply means that you must describe your invention in such a way that someone can repeat it. So the level of detail is very similar to the level of detail for a journal article, But remember that sometimes the journal article describes the scientific discovery and not the actual claimed invention. So that level of detail must also be provided for the method or the composition that you are actually claiming. And sometimes in the case of my example with the cancer, X binds to Y in a cancer cell, but the claimed invention is a method of treating cancer or a method of diagnosing cancer. You may not know that detail. I mean, that method, that therapeutic application may be several years down the line. So how do you fulfill the enablement requirement here? And this is it's a little bit of science fiction sometimes. You have to write prophetically the way you think you would use it, the way you think the therapeutic method would be carried out in as much detail as you possibly can. And with the knowledge that you have, that is likely going to fill the enablement requirement. But sometimes it is a challenge because there is a gap between scientific discovery and actual practical application of an invention. So taking this down just a little bit more, what does new mean? I mean, it's pretty obvious, but generally, the statute is copied here, but generally it means what is prior art? New means, prior art is anything that is published before the filing date of the patent application. So some common public disclosures. Publication of a scientific journal by mail, well, that's outdated. Few people get them by mail anymore. Internet posting. When does it get posted on the internet and is available to the public? And that doesn't mean general public. If you are a subscriber, that's considered general public. One thing to keep in mind here is sometimes abstracts of accepted papers are published a little bit earlier than the entire paper. That can often serve as prior art that can be very damaging for a patent application. So not only do you want to ask your publisher, when is the entire paper, including figures and supplemental information, et cetera, when is the whole thing going to be put on the internet? You also want to ask, are you going to put the abstract on before you publish the whole thing? And that will be the operative date. Scientific meetings, verbal communications like talks at a scientific meeting are most certainly a public disclosure. Something to keep in mind, slides on a screen are ephemeral. They're up only for a couple of seconds. So in terms of a valid prior art disclosure, there's actually been case law on this. If someone flashes a sequence, an amino acid sequence of 5 to 10 residues on a screen, that has been considered valid prior art that can be used against you. However, if that slide that's up there for probably 30 seconds or less, if it contains 500 residues or 1,000 residues, that has been deemed to be not usable prior art because it's so ephemeral. No one could have jotted down or gotten the gist of, in a practical way, that information, whereas 5 to 10 amino acids most certainly can be captured by the human brain. Posters, even though a corresponding abstract or replication of the poster has not been published in a journal, posters are most definitely fair game because it's displayed for a long period of time. Oops, I think something just happened here. A long period of time. Someone can take a picture of it. Someone can take a photograph of it. And of course, another caution is when you're going to submit your abstract to the meeting administrators, always important to ask them when the abstracts are published online. Sometimes they're published all at once, and they will give you a date. Sometimes they're published on a rolling basis as they are accepted. That's a patent attorney's nightmare, and but you want to know that. Not so common public disclosures, and I call these stealth disclosures. In the United States, when you apply for federal funding, you write a great big grant application. Very often you speculate wildly because you're asking for money to do all of these different experiments. So there is lots and lots of really useful information in there. it becomes valid prior art as of the grant date. So important to ask when that grant date will occur. Even though the general public cannot gain access until several months later, the legal aspect of it is under the Freedom of Information Act in this country. The entire thing is public information with one caveat. If someone wants to get a copy of it, you, the applicant, will get notification that someone has requested a copy of your grant application, and you will be given the opportunity to redact financial information, salaries, and requests for, for money, and you also will be able to redact things that are directly related to commercialization, but that's a very fuzzy term. In other words, you will not be able to redact scientific information, what you're, essentially proposing to or asking money for. So all of that good speculation and definition of experiments, that will all be fair game. So very important to keep that in mind. Graduate student theses. Very often in this day and age, there's many publications, journal articles that come before a student thesis or a defense. However, just wanted you to know that the prior art date of a student thesis is the date upon which it is cataloged and shelved in the university library, that is the granting institution. Clinical trials also can be published. And then something I didn't put on here, but something to be careful of, there is an old case, and I'm sorry I don't have a citation for it, and it was a long time ago, over 10 or 15 years ago. A patent was knocked out because there were two scientists at a meeting on a bus discussing their research without, of course, saying this is a confidential disclosure. And those two people heard it, and as did all the people around them heard it. And that information was used to knock out the validity of a patent, an issued patent. So important to keep that in mind. Okay, the next requirement. We talked a little bit about enablement before. We don't have to talk about it again. Written description. It's under the same statute as enablement, but it's a little bit different and very important for claim scope. We all want to get the broadest claims possible, and so we try to write in generic terms. So, for example, the genus might be an antioxidant, the use of an antioxidant to treat some disease. That's what we're trying to claim. So say your specification, your description, disclosed one example of an antioxidant. It disclosed ascorbic acid. So the broadest claim is before the examiner. The examiner says, a method of treating dread disease X by administering an antioxidant. Then the next claim is wherein the antioxidant is ascorbic acid. So we want to get that broad claim. The examiner will come back and say to us, well, you described ascorbic acid. I will give you a claim that says the method of treating this disease by administering ascorbic acid. I will not give you the broader claim breadth. I will not give you the genus of antioxidants because you have not shown me, you have not described a representative number of species within the genus. You would be up a creek. You would not get that claim unless, for example, in the specification, even though you hadn't done experiments with it, if you had described, for example, not only vitamin C, glutathione, malathione, taurine, alpha-tocopherol, resveratrol, lycopene, 3 to 5 examples of what antioxidants could be used, then you can argue back to the examiner, oh no, I have described a representative number of species within the genus, and you will likely overcome that rejection and get a generic claim, which is the goal, the holy grail through all of this. Okay, next here. 101, what inventions are patentable? And this has been a rarely used ground for rejecting claims. What is patentable subject matter? Well, as I described to you before, a mere discovery or an idea, not patentable. Mathematical algorithm, not patentable. This has come in the forefront just in the last year and a half, and all of a sudden, lots of claims are being rejected under 101 unpatentable subject matter. And the reason is a case that came down, it was actually in the Supreme Court last year, the Prometheus case. And that now says, of course, we all knew before, laws of nature also fall under unpatentable subject matter. This case deemed that methods of diagnosis are unpatentable subject matter because they are merely an identification of a law of nature. So there are lots of methods of diagnosis, issued patents floating around out there that their validity is in question. So now, but going forward, as we go ahead and try to patent methods of diagnosis, how do we get around that? There are a couple of hints, and none of this is settled because the case is fairly new and there hasn't been much activity or no activity really subsequent to this case, so it all needs to be tested. But a few, so an example, method of diagnosing cancer by detecting an increase in the protein X. The patent office now will say, no, that's not patentable because the presence of an increase in protein X is a law of nature. It's a natural phenomenon. So how do we get around that? One way to get around that is to invoke a new and non-obvious detection reagent. And a second way is to define in your method of diagnosis something that does not occur in nature in the human body. So, for example, a method of diagnosing cancer by contacting serum with reagent X, and that reagent X needs to be something new and non-obvious that has not been used before to detect this protein. That gets you out of the law of nature. The other way to do it is in detecting, not just simply detecting it in serum, but detecting, for example, a complex that is formed between protein X and your new and non-obvious detection reagent. So that particular complex does not occur in nature, does not occur in the human body, likely will get you out of this unpatentable subject matter dilemma. Okay, as I mentioned earlier, most of the patent application is description, enablement, and written description of that which you're trying to claim. The claim is really where the money is. This is the last couple pages of a patent application or patent, and this is where your legal rights are. And what I'm going to go through next is just kind of an interesting and fun exercise, because usually what happens here is we try to write the broadest claim we possibly can, and it's actually quite rare that what gets granted or issued is the claim that one originally filed. So here's some examples. Excuse me. Say you discovered that this compound X specifically kills cancer cells. It doesn't kill normal cells, so it looks like it's going to be this really great cancer drug. So you figure that you discovered this compound. So we file a patent application in the patent office saying, simply, plain and simple, a composition comprising compound X. We feel like we're entitled to it because as far as we're concerned, we were the first ones who came up with this. We made it, we think it's new. Well, lo and behold, patent office goes and does a search, and the patent examiner finds compound X was used in some previous publication in pick something crazy, something very different, non-clinical, non-medical, say in paint solvent. But lo and behold, compound X was known, and it was known in paint solvent. So how do you get around that? The claims that can issue here are, we can get around that by saying a pharmaceutical composition containing, for example, this compound. We might even want to say a certain amount, but I think we can even get away with saying a pharmaceutical composition because it would be completely unreasonable, crazy, and not of skill in the art to take a paint solvent formulation and administer it to a human being. So one way is to call it a pharmaceutical composition or say it is in a pharmaceutically or clinically acceptable excipient. We can give an amount. These are all ways to sort of get around a piece of prior art that might knock out what you thought was brand new. And another way, of course, would be to claim it in the form not of a composition, but of course to claim a method of treating cancer, inhibiting tumor growth by administering compound X. That piece of prior art where X was in a paint solvent would certainly not render this method of inhibiting tumor growth as being not novel or obvious. More examples here. A medical device containing structural element A and structural element B. What if the examiner does a search and finds a piece of prior art, a publication that shows that a medical device showing A plus B plus C? Well, A plus B, that's what your first claim is, so you've got a problem there. One way to get around it is to make a negative carve-out. You can say, I want to claim a medical device containing A, B, and not C. The kicker here is you have to be sure that C is not a critical component. And secondly, and more importantly, for when you are drafting the patent application, this negative carve-out can only be made if you specifically state it in the specification. So that speaks to sort of predicting what elements are key, what elements are optional, and if you in fact come across a piece of prior art, then you put in that language that allows you to write this negative carve-out language, and then you can get a patent. If not, you may end up with nothing. The last example here is method of drug delivery comprising contacting a subject with the device of claim 1, and your device has got some sort of micro or nanoparticles. This actually happens a lot. A prior art reference is found either by you or by the examiner that gives a very large range of size of these particles. So the originally filed claim is probably unpatentable. It would be very difficult, if not impossible, to get. So you need to narrow it. And again, this speaks to having foresight when we write these patent applications. Sometimes we write what to an inventor looks like arbitrary ranges of components, physical and structural attributes of compounds or in this case particles. And so in this case, we could get around that publication, that prior art, by, for example, limiting the size. Here in the example, I say does not exceed 100 microns in size. We could also do something like, between 20 and 100, between 20 and 50 microns. This is where the patent attorney works with the scientist to say, okay, what's the optimal range, and what are ranges within reason that essentially represent then fallback positions if you get hit with some prior art, some prior publication that discloses some, but not all, or perhaps not as much detail as you want to claim or that you will find useful in a commercial setting. I'm going to switch gears here a little bit to talk about documentation of the inventive process. What do you need to do? First one's pretty obvious. Keep proper lab notebooks. Everybody does that, of course. The next one is more important, and fewer people do this. And it's important because it can establish a much earlier conception date, priority date, and that is keeping notes from brainstorming sessions or discussions in maybe like an idea notebook. This is important because it's information that likely will not end up in a lab notebook unless you keep ideas jotted down in your lab notebook because the experiments haven't been done yet. However, sometimes you might need to prove that you conceived of the invention, you conceived of a certain or predicted a scientific discovery long before you actually did the experiments and showed that it was true. So that's an important thing to do. Computer entries, very often they're iterative. It's important to document each iteration because as the discovery, be it a sequence or be it just a characterization of something, it can evolve over time. Sometimes one might need to prove what we knew at X date versus Y date to perhaps prove that we invented first. Publications options, we already talked about that. Inventorship, not only do we need, this could be a whole separate talk, right, Michelle? We could talk, for an hour on inventorship, but the only point I'm going to make here is inventorship needs to be determined. It's not the same as authorship. Maybe they'll invite us back and we'll talk about inventorship. But the important thing here is to keep track of, as the invention or the discovery unfolds, who did what when. And the reason for that is inventorship is determined on a per claim basis. So we may have 10 claims, and person A and B and C might be an inventor on claim 1, an inventor D and E on claim 5, and some combination thereof for intervening claims. If claims are changed or canceled, we have to change the inventorship to make sure it's accurate.
Shmulik, we started a little late. I was just trying to see how we want to manage time. Are we able to run over, or should we just limit ourselves to the original time frame? Are you online? Can you answer that?
Michal, most people are Michal, can you hear me?
Yes, Sigal.
Okay, so most people are on their lunch break, so if you need to take a few more minutes, it's fine. If you feel like we should do another webinar with you and let Ingrid have the full hour, that's fine too.
We could do that. I think that we'll let you, because I think Ingrid could easily run through
at least 15.
At least 15, and if we want to have mine on a different day, that's fine.
Okay, so I'm getting it. So let's get back to Ingrid. Sorry for the break, and we'll have this later. Okay.
Okay. Apologize, and I'll try to run through these last couple slides quickly. And if there are any questions, of course, at the end, we can deal with them, or you can email them to the meeting. Quickly, before filing, what are the kinds of things that you do? We talked about some of this earlier. Some of it really is predicting the future. And since we want to claim the most broadly the genus species thing, in addition to exactly what we plan on commercializing, we want to give lots of examples. And sometimes you don't have the examples, so you have to write them prophetically. So in the example of the X binds to Y in cancer, you may not have inhibitors. You may just have the observation. So one way to handle that, to try to predict and write into the application what inhibitors might look like, you can look at these proteins, and you can perhaps even if there was not if their crystal structure available, you could of course get a sense of the of contact points. But even in the absence of crystal structures, you might be able to take a look at the sequences of these two proteins and predict how they might interact, or predict which residues look to be on the outside versus the inside of the molecule, and then you can prophetically write examples of inhibitors based on what they bind to. And again, alternative claim language, giving lots of examples. Anything, I guess the best way to think about this is, if you were a competitor and you were trying to design around a patent claim, what would you do? And if you do this at the stage of before filing, you can write all these backup plan kind of strategies into the patent application and use them to enable your claims and also to provide a much broader claim scope. Again, this is perhaps self-evident, but it doesn't always happen. During the prosecution of a patent application, which can span several years, it's important to communicate business objectives to the attorney and also to the technology transfer people, because during those several years, things may change. For example, there may be a best mode. You may have a favorite compound that works really great in your cancer therapy, and then after a couple of years of experiments, you may find that a slightly tweaked or changed compound, or maybe a different compound altogether that hopefully was in the original patent application, but maybe you switched from, favorite compound A to favorite compound B, you want to make sure that the patent attorney knows that and changes their strategy to keep pursuing that which is going to end up in the clinic and ends up, being commercialized, rather than fighting to the death for a compound that the inventors are no longer interested in. Same with whether to republish. If the claims change substantially, one may want to republish the patent application to get intervening rights. Once a patent application publishes, that puts the world on notice as to what is likely to issue. And then lastly, as I mentioned, inventorship. If you cancel claims, if one changes claims, one has to re-examine the inventorship. I think the next slide I'm actually going to skip. The next couple of slides are really a lead-in to Michal's presentation, which has to do with commercialization of university-developed technology. And that is governed by the Bayh-Dole Act if the research was carried out under federal funding in the United States. And the bottom line of the Bayh-Dole Act is that the title of the inventions, as I mentioned earlier in my talk, must be assigned or given over to the recipient of the federal funds, meaning the university or the academic institution. And there are other things. The university then, in turn, goes out and seeks a licensee, seeks a commercial partner. The inventors are the royalties that come are shared, and Michal will give some more details and examples of that. And if there was federal funding involved, one thing that is mandated is the university must try to commercialize it in the United States. That's not an absolute. It can be commercialized with a foreign entity, but they at least need to try to develop in the United States. The last couple slides here are, for no other reason, I'm not going to go into, the pipeline or the development line from discovery to drug. My only point with these next two slides is to simply say to you, it takes a long time. It takes a very long time, and as you know, the term of the patent runs from the filing date, and so, as we're going through the pipeline from a discovery to a drug, the clock is ticking, and the patent term is becoming less and less valuable because there aren't that many years left. So the important thing to do is build and maintain a strong patent portfolio, and that is done by continuing to file additional patent applications, be they improvements or be they slight changes in formulations or delivery mechanisms that will stand up and be patentable in terms of new and non-obvious over your original filing, but have the advantage of taking your patent protection out further and further into the future as you go through the drug development pipeline. And the other thing to understand here is not only do you want to file patent applications on what you are going to do, you might want to file patent applications on things that you suspect others will do to get into your commercial space. So you may not necessarily practice them, but you might want to write applications that, for example, would try to cover those strategies that you have thought of that your competitor might try to use to get around your primary patent. And that's called sort of building a picket fence. You're making it very, very difficult for your competitors to get into your backyard by constructing this picket fence. And with that, I will close and hand it over to Michal, who will tell you quite practically how to take your invention from the lab to the real world. Thank you very much.
Actually, I think we should probably take questions now because we're going to run out of time. And let's open it for questions to Ingrid. I'm not sure how we're getting those. Are we getting those in writing?
Sure, either. I won't be able to pick them up on this video. Gal, can you guide us? Are we,
Yeah, here. Can you expand about algorithms, software? So I think
yes.
everybody can see the question. But
Yep, so the question is, can you expand about algorithms, software patentability, copyright versus patent? Algorithm all by itself, not patentable. The practical application of it, how you would use it, and so for example, you say software here. Software can be patented. It is obviously quite different than writing biological clinical kinds of inventions, and it is certainly not my forte. That would be more of an engineer that does that. But for example, software can be claimed and can be described sort of in a flow chart. It does not have to, every detail does not have to be described in a description of a software patent. I can send you, if you send me your email address, I can send to you some examples of what these sorts of issued patent claims might look like. And also what some people do is with software, they will publish and copyright like every third page or every X page of the software code. So the entire thing isn't given away, but you do still have some protection there.
If you don't want to file?
And if you don't want to file, you don't file because...
But then you still have copyright.
Right. And the problem with those sorts of inventions is the field changes so quickly and the patent process is so slow, a lot of people actually choose not to file because of that reason. Closer into the microphone. Is that... I haven't seen any more questions, so if there are questions, feel free to email me and I will do my best to get back to you. Thank you so much.
Okay, great. Thank you, Ingrid.
So maybe since we have a couple minutes, maybe I can just briefly give an introduction to what may be the next webinar in which I can actually go through my entire presentation. Is this useful, Sigal?
Yeah, I think it is because it will give people an idea of why they want to join.
Okay, so what I think would be useful for the group, and I see some familiar names, so hello friends and acquaintances from across the globe. I think that what I would like to cover are very practical descriptions of the process of moving an invention from the lab toward a product, both in the context of an academic lab and, as I see a few people here who actually maybe no longer in an academic lab but are independent, then maybe compare that to a situation in which somebody is actually working on their own. And I think there are some differences. So, for example, Ingrid talked about the timeline and the timing for protecting an invention. In an academic setting, many times we're bound by the academic environment. So the most important thing is to publish and talk about your work, and that means that sometimes you have to protect your invention very, very early, much earlier than would be optimal from a business perspective, because you're not ready yet. You don't really have the product yet. You have not enabled yet. You have not reduced to practice. You don't know what compound is really the powerful one and which are the backups and so on. But you have to do it because you're about to publish or to talk about that. When you're an independent, you can really control that time frame. So there are some distinct differences, and I will talk about those. And I will talk about forms of scientific entrepreneurship. So from my perspective, and I think when people talk about entrepreneurship, which is the title of this webinar, many times they think startup. And I don't really think that that's the only form of entrepreneurship. I think it's one. but you can be extremely entrepreneurial as an academic investigator in conducting entrepreneurial research in your lab, or collaborating with companies, or being engaged in kind of co-development projects with different partners. So I will touch on that because I think it's important. Not every one of us is kind of cut the same way. We don't have, we have diverse personalities and objectives and priorities, and I think that still every one of us can be a scientific entrepreneur if we choose to, in our own way that we choose to do that. And I'll talk a little bit about launching startups and what that takes, and I will give you my practical advice from, I guess, both seeing many different technologies that move in that direction in my day job, and also from having done this and participated and continuing to participate in companies that are being launched. So I think that will be kind of in a nutshell what I'll talk about. I think that we are I think we had a slightly different plan, but hopefully this was interesting. I think that the one message that I would say is that we need to remember that as complicated as patenting may be, if we want our invention, if we want our discovery, if we want our vision to move toward a product, it is a necessary step, and there are many qualified people around you, around each one of you on that list of names on the left there, who can help you navigate through that and go through a successful process. And the one thing that I would say, and this will be covered in my talk, I guess, when we have it, is that if we choose carefully what to focus on, and that is part of the art, right? So not every scientific discovery that you will be making or have made warrants this process, and maybe the first thing to do is to really kind of consider what would be the opportunity on which you want to focus and make the effort to move it from the lab to the product. But once you evaluate that this is a good opportunity and get a reality check from the outside world, then the way will be found to make it happen. So I hope you are left with the right impression that this is a process that has many that is both an art and a science, but there are good people who can help you make this, I guess, take care of that aspect of entrepreneurship, which is necessary. It is, from my perspective, a vehicle toward a cause, and not a cause in itself, but it's something that is doable. And again, I think we're probably just about done, but if there are any final questions to Ingrid or to myself that we can cover today, then I think we could probably take one or two additional ones. Okay, so if we don't have any, thanks Ingrid for being my partner in crime here. I think we'll work with Sigal to maybe schedule another time for the second piece. I hope to have some or most of you back for that seminar, and
Okay, Michal, Ingrid, thank you for coming on this snowy morning.
Yes, thank you.
Thank you.
To a rainy afternoon.
Right.
Yeah. Here from sunny Tel Aviv, well, it's evening, but it was really a beautiful sunny day. So,
Oh, yes. Okay, well, thanks everyone for attending. We certainly appreciate so many of you showing up. Thank you.
Absolutely. Thank you.
yeah, thank you very much, everyone. Bye.
Bye-bye. Monitor this.